Logistic regression is one of the most important statistical methods for health research. Instead of predicting continuous outcomes like blood pressure, it predicts categorical outcomes. For example, whether a patient develops coronary heart disease or not. The patient will, what are the probability of this patient staying 5 years from now or not. We can use one or more predictors, and these predictors can be continuous like age or cholesterol, or categorical like sex or smoking status. Ordinary least square works great when outcome is continuous like blood pressure. But when it comes to outcome which is binary, say yes or no, or live or dead, a disease will happen or not, we are in fact predicting probabilities which must stay between 0 and 1. 0 being there is no probability of that event being happening, and 1 being 100% probability of that event being happening, whether it is the development of cancer, or it is the probability of surviving or improvement. Whatever is the probability, it is between 0 and 1. And ordinary least square can give us invalid results. Say it might give you a result of minus 0.2, which will make no sense in terms of probabilities, or 1.3 or 2.4. 2.4 will have no valid interpretation when it comes to binary outcomes, yes and no. So we need a system where the results are between 0 and 1. It can give us the probabilities of happening or not happening, or what are the exact precise risk of that event happening. So that's why OLS isn't suitable for categorical variables. Let's try to understand why ordinary least square OLS cannot be used for binary variables from this example. The hours studied by the students and their passing results, yes or no. Suppose the first student who couldn't study at all gave the exam and was not able to pass. The second student, he or she studied for an hour, and again she was also not was able to pass the exam. The third studied for 2 hours, was not able to pass. Fourth studied for 3 hours, but that person passed. Then the fifth person studied for 4 hours, couldn't pass. Sixth person studied for 5 hours, they passed. Seventh person studied for 6, passed. 7 couldn't pass. The person who studied for 8 hours passed. The ninth person or 10th person who studied for 8 hours, this person also passed. And the person who studied for 10 hours, this person also passed. If we plot all these values on a graph, say the probability of passing on x-axis and the hours studied on the y-axis, the first person who did not study and unfortunately couldn't pass will be represented by this dot. The second person who studied for 1 hour but couldn't pass is represented by the second dot here. Third person here. Fourth person who studied for 3 hours but was able to pass the exam will be represented at 1 right here. Fifth person who studied for 4 hours didn't pass. Sixth person, seventh person, eighth, ninth, 10th, and 11th person. We see that the people who studied for 8, 9, and 10, they all passed, but the person who studied for 7 hours did not pass, and so on. Now, if we try to represent all these lines with a single line, it will look like something in a shape of a sigmoid. And we can see that it is more pulled down by most of the red dots at the bottom, or the people who have 0 value of passing, and then it is pulled to the top by the large number of people who passed and have higher number of studied hours, and in between it is kind of a steep. Binary outcomes behave very differently from continuous outcomes, and they introduced three key challenges. So challenge one is that of bounded probabilities. As we discussed previously, the probabilities have to stay between 0 and 100%. And in case of ordinary least squares, it can give us the values 1.3, 2.5, which would make no sense in binary outcomes. And similarly, it can give us minus 2.3, minus 5, whatever. So those values will have no meaning in case of binary outcomes. The second challenge is non-linearity. Binary outcomes don't follow a straight line, as you can see in the graph. Instead, they follow an S-shaped curve, right? The sigmoid shape. This means that the effect of predictors is not constant. They vary depending on where you are on the curve. For example, um, the increase of study from 1 to 2 hours have very little effect, maybe just 5 to 10%. But when it is increased from 5 to 6 hours, there is a big increase, almost 40 to 50%. So the effect of predictor is strongest near the 50% probability. The third challenge is a violation of error assumptions. In OLS, ordinary least square regression, we assume that residuals are normally distributed and have constant variance. For example, all these values will be normally distributed along the line. But with binary outcome, this isn't true. They follow a binomial distribution where variance changes depending on the probability level. They are more unreliable, close to the 50% probability, when we see that they are higher variance compared to both the extremes. Logistic function solves all the three challenges in one shot. First off, it transforms the probabilities 0, 1 into continuous log odds, which extend from minus infinity to positive infinity. Number two, it keeps the predictions bounded between 0 and 1. And then it models the S-shaped sigmoid curve naturally. And it also correctly handles the binomial error structure. The logit function is the foundation of logistic regression. It converts probabilities, which are always between 0 and 1, into log odds. Log odds have no bounds. They can range from negative infinity to positive infinity. At a probability of 0, the logit equals negative infinity. And at a probability of 0.5 or 50-50, the logit becomes 0. And at a probability of 1, that's 100%, the logit equals positive infinity. So this transformation stretches the bounded probability scale into unbounded scale. And it allows us to use a linear model for probabilities. But again, most importantly, it ensures that all predicted values remain valid between 0 and 1. Okay, let's compare probability, odds, and the logit function. At 0% chance, the probability equals 0, the odds equal 0, and the logit goes to negative infinity, as you can see in the figure right here. Right? At 50% chance, the probability is 0.5, the odds equal to 1, which is the neutral value for the odds, and the logit function will be equal to 0. Again, take a look at the figures on the left. At 100% chance, the probability becomes 1, which represents 100%. The odds reaches infinity, and the logit function reaches positive infinity. So notice how the logit function stretches the probability scale into unbounded scale. The probabilities are trapped between 0 and 1, and odd ranges from 0 to 1 on the negative side and 1 to infinity on the positive sides. But log extends across the entire real line from negative infinity all the way to the positive infinity. And you can see the same thing in the figure on the left. Okay, so this is what makes logistic regression possible. It converts the unbounded probabilities into a form that can be modeled linearly. So the logistic regression always predicts probabilities between 0 and 1, and this solves the problem of invalid predictions such as negative probabilities or values greater than 1. The logic itself can take any values from negative infinity to positive infinity. Because we use the formula here, we are taking the natural log of p, that is the probability, over 1 over p, which is the probability of not happening. So probability of the event and probability of the event not happening, and these values will always remain between negative infinity and positive infinity. But when we invert the logic, the result is always a probability between 0 and 1. That's why logistic regression produces valid and interpretable outcomes. The probability curve from the logit function is naturally S-shaped or a sigmoid shape. The slope is steepest around 0.5. This means that a small change in predictors near 50-50 threshold produce large change in probability. Near the extreme, the curve flattens, right? If someone already has a 95% chance of disease, adding another risk factor will hardly change the probability. This matches reality. Probabilities change rapidly around the middle but stabilize at the extremes.